welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings, or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Today's topic, Coherent detection of polarization, multiplexed, amplitude, and phase modulated optical signals. I will give a brief agenda of today's talk. So first, after a short introduction on the topic, what is polarization multiplexing, I will give you a few slides on complex modulation, how it increases the efficiency of signal transmission, of digital transmission. I will then introduce a little bit of math and physics, how signals propagate on single-mode fiber, and introduce a little bit of Jones calculus. And after that, I'll give you a short introduction on coherent versus direct detection, how this affects the signals you can receive, and how this affects the measurement hardware. Then I will show how the instrument to measure these signals could look like. And we have just recently on OFC introduced an instrument that can do this. I will then switch over to an important algorithm that is needed to decode these signals, which is called channel matrix estimation. I will then show a few measurement examples, and finally end up with a short conclusion. So fundamental directions a network right now takes. Of course, reducing cost, being cost effective, is always an issue, and photonic integration and power consumption are a few things people look at. Of course, also people look into flexibility, switching the optical domain, an all-optical network. So they are looking at the configurable optical add-drop multiplexers, tunable transponders. But today's topic is in this area, so it's all about capacity and speed, how we really can support the increase in traffic we are seeing in the networks, and traffic is still growing, especially in the 40 and 100 gigabit per second transmission speed. People are talking about advanced and complex modulation techniques, and polarization multiplexing is one means to increase the efficiency of transmission of digital information. So very briefly, how complex modulation really works. So all you want to do, of course, is transmit a binary bit stream. So in case of a QPSK signal, which is depicted here, the binary bit stream is demultiplexed into two bit streams, half of the bit rate. So there's a bit stream up here and a bit stream down there. Then there is a laser that serves as a carrier for the transmission of the signals. Then the binary bit stream is amplified. So you have an analog signal. And these analog signals for the demultiplexed bit streams are then encoded using a double mass sender structure. So there's one mass sender modulator over here, and there's another one down here. There's another pi-half phase shifter, so that both bit streams coming out, signals coming out of the mass sender modulators are shifted by pi-half with respect to each other, and then those two signals are combined, so you end up with a QPSK signal. So looking into detail what is coming out of the first mass sender structure, in case of a 1, there's a cosine phase. So you start up here and go down there. And then if you switch from the 1 to the 0, there's a 180-degree phase shift. And if you stay from the 0 to the 0, there's no phase shift down here. And then if you switch from 0 to 1, there's another 180-degree phase shift up here. That's the upper arm of the modulated structure. And in the lower arm, you start with a 1 again, but this time you have a sign because of the 90-degree phase shift up here. And switching from 1 to 0, there's another 180-degree phase shift, so it's a minus sign, another 180-degree phase shift plus sign. So if you add up those two, which you do up here in the modulator structure, you end up seeing these waveforms coming out of the modulator. So there's a 1, 1, then there's a transition to a 0, 0, which is in the constellation diagram from upper right corner to lower left corner. The constellation diagram is an easy means to visualize the constellation or the phase of the signals. So you could look at this as the in phase and the quadrature signals. And so in this case, you have a 45-degree phase, which is exactly what you have here. And then you have a transition from 1, 1 to 0, 0. you have the phase shift of 180 degrees. And then from 0, 0 to 0, 1, you have a phase shift of 90 degrees, which is what you see here. And from 0, 1 to 1, 0, you have again a 180 degree phase shift, which is what you see here. So polarization division multiplexing, it's all about increasing spectral efficiency. Since the optical wave is a transverse electromagnetic wave, you can split this into two orthogonal polarizations, and you can modulate a signal on each of these polarizations. That's why you can carry an independent signal on each of these two polarizations. Therefore, you can look at the fiber as if it had two virtual channels to transmit basically two of the signals. At the receiver, then, you can split the signals again into two polarizations and recover the original information sent out from the transmitter. So, bottom line, the polarization division multiplexing, PDM, increases the spectral efficiency by a factor of 2. It's depicted down here. So you have your well-known WDM channels. You have one channel in the Y polarization, and at the same wavelength, you can send a different signal on the X polarization. That's why you have the increasement of a factor of 2. So what does that mean for the spectrum of the transmitted signal? If you start out using a classical on-off keying signal, in this case it's a 112 gigabit per second spectrum centered around the optical carrier. You have a spectrum that's basically 2 times the bit rate of your transmission. So it's 224 gigahertz wide, the spectrum, until you reach the first minimum. Now if you increase the spectral efficiency by a factor of 2, because you're switching from on-off keying to QPSK. In QPSK, you can transmit 2 bits per symbol, which basically increases your spectral efficiency by a factor of 2, because at the same symbol rate you can transmit basically twice the amount of information. That's why the spectrum, if you switch from 112 gigabit per second to 56 gigabaud per second, each symbol carrying 2 bits, you end up with a spectrum that's 112 gigahertz wide. And then there's another factor of 2 if you switch from single polarization to polarization division multiplexing. So you end up with a spectrum that's 56 gigahertz wide. And if you look at this spectrum, the information is confined in the inner half of this. So the actual transmitted wavelengths or the actual transmitted bandwidth you need is 28 gigahertz. That's why this fits into a 50 gigahertz ITU channel. So bottom line, using advanced modulation and PDM, you can transmit to 100 gigabit per second in a 50 gigahertz ITU channel, and that's what is deployed in many of the networks you see right now. So let's briefly look on how the signal propagates on a fiber, especially in the case of polarization multiplex signals. Standard single-mode fiber is not preserving the state of polarization, and so what does that mean? If you start out with a polarization X pointing in this direction and polarization Y pointing in this direction, and over the course of time or along the fiber, the polarization starts to rotate, first to the right and then to the left. So finally, at the receiver, you cannot tell in which direction the X polarization of your signal and in which direction the Y polarization of your signal points. And to describe this effect, to describe the properties of the fiber, you can use the Jones calculus, and I will introduce this Jones calculus in detail in the next slides. In contrast, polarization maintaining fiber, PMF, preserves the state of polarization, but as a matter of fact, today's networks do not have these fibers deployed for transmission of signals. So a very simple example of a few Jones matrices are now presented in the next slide. In this case, we have an ideal transmission channel. So you start out with an X polarization and Y polarization at the transmitter. Then there's an ideal transmission channel, and you have an X polarization and Y polarization at the receiver. So the sent out signals are described by S, X, and SY, and the received signals are R, X, and RY. And an ideal transmission channel just propagates the S to the R for X and the SY to the RY for Y. In this case, it's a unitary matrix, and it's a very simple math, of course. One has to note that Sx and Sy are time-dependent complex numbers describing the field, as was introduced previously on the slide around complex modulation. It's really describing the field, including the phase, not the optical power only. In this case, where transmitter and receiver frames are aligned with respect to each other, the signals are identical, so there's no need to decouple those. There's no crosstalk between the virtual polarization channels. Now, in case where there's rotation of the polarization, like I described on the slide about signal propagation on a single mode fiber, there's a rotation of the polarization. So you have, again, starting at the transmitter, the X and Y polarization. But in this case, the X and Y polarization of the receiver is slightly rotated by the angle phi. And the Jones matrix for this propagation is a simple rotary matrix. There's only one independent parameter for this, and you can easily recognize the rotary matrix here. In this case, of course, if you look at the received signal Rx, you see the Sx of the transmitter and you see a Sy of the transmitter, and they are intermixed, and the angle of rotation describes the mixture of those two signals. However, without loss PDL and PMD, the channel matrix is still quite simple and has only one independent parameter. It's the angle of rotation of the transmitter frame and the receiver frame. If you now look on why do we need to measure field, or what's the benefit of measuring field versus measuring the power, if you look at the simple on-off keying signal on the SY and SX channels, there's a 1, 0 on the X channel and a 0, 1 on the Y channel. And then in this case, I have chosen a rotation of 45 degrees. So the receiver is rotated 45 degrees with respect to the transmitter. So the sent out signal in black again is rotated 45 degrees with respect to the receiver frame. And in this case, on the Rx of the receiver, you receive the same for both signals because it's always pointing in the same direction. But on the Y channel, you receive 1 over square root of 2 for the 1 of the SY and minus 1 over square root of 2 for the 0 of the SY. So there's clearly visible a difference in the field measured at the receiver. Now, if you look at the power you would measure using these fields, you don't see a difference because the power is the field times the conjugate of the field. So in this case, it's 1/2 for this combination, and it's 1/2 for this as well, because building the power, it's times the complex conjugate, so it's always a positive number. So in this case, you have completely lost any information. You have the same received signal regardless of what you have sent out at the transmitter. So by detecting the power, the phase of the field is lost, and that's the reason why you cannot resolve any polarization division multiplex signals using power detection in contrast to field detection. Now, if you add loss and PDL to your transmission link, you can easily look at this using this graph. So there's a signal coming in on this polarization and on this polarization, but you have different attenuation constants for those two polarizations. There's an alpha S for this and an alpha P for this. So if you look at the mass again, so you have an SX and SYS from the transmitter, then there's a rotational matrix because the principal values of the PDL need not be aligned with the transmitter frame. So you have to rotate first the signals to match the transmitter, the PDL principal axis. Then you have the loss and PDL of the two signals. You recognize the alpha S, the attenuation on one channel, and the alpha P, the attenuation on the other channel. And then again, there's a rotational matrix to rotate the principal axis of the signals to the receiver frame. So in total, you have 4 independent numbers to describe the channel matrix, or the Jones matrix in this case, and PDL. In this case, of course, destroys the orthogonality of the signals. In a worst case, where there is a polarizer, then of course the two signals from the transmitter will collapse to one polarization at the receiver. Now finally, if you add P and D in addition, and you look at the transmission matrix, you end up using the full Jones matrix, which is a complex value 2x2 matrix. So there's a total of 8 independent real parameters for this Jones matrix. And that's what you also find in literature. In this case, It's from a publication in Photonic Technology Letters, Channel Parameter Estimation of Polarization Diverse Coherent Receivers. In this case, you have polarization state transformation, which is what we have shown before. But in this case, there's a PMD inside, and of course, you have the PDL in this case. And that's what we are focusing, how we can really resolve the signals if we have these kind of distortions on your transmission. So to really get the send-out signals from the received signals, you really have to solve two problems. The first is you need to be able to get an estimate of your transmission matrix, your Jones matrix. And then what you can do, of course, you can calculate the inverse of this Jones matrix, which is this expression. And then using this inverse of your Jones matrix, you can use your received signals, multiply it by the inverse of the Jones matrix, and get back to your send-out signals from your transmitter. And the second, of course, as I've shown before, you have to measure the field and not the power, so you need to be able to measure the field, and that includes the phase of the field, of course. But again, from this publication, what we are looking at, so we have a transmitter, we have the fiber channel, the transmission channel, we have an A to D conversion, and then we have, in this case, a butterfly equalization filter. And we are looking at the simplest form of this equalization filter, which has only one filter tab, and that's the inverse of the channel matrix. That's exactly this expression. And then, of course, you have to do, in case of a coherent receiver, carrier recovery and decoding of the signals, so you finally get your digital information back. So the coherent receiver is able to detect the field and not only power. So this coherent receiver will solve the problem to measure the field and not the power. So comparing coherent reception versus comparing direct versus interferometric detection. So in direct detection, you have just the optical signal impacting a photodiode, and to measure what the photocurrent of a photodiode puts out, it's quite simple. So you have to just multiply the signal and the complex conjugate of the signal. In this case, the signal is just the product of an amplitude term here, which is a real number, and the phase term. And the phase term is split into a static phase and a time-dependent phase, which is the frequency of the signal. And if you do the complex conjugate multiplication, you end up with just the square of your signal amplitude. So the field, the phase of the optical signal is lost, so you only measure the optical power. So direct detection does not help you in measuring the phase. If you do interferometric detection, then you have a signal and a reference signal. You mix it using a 3 dB coupler, and then there's two photodiodes. And on the photodiodes, you measure on the one photodiode S plus R, so signal plus reference signal times S plus R complex conjugate. And then the other photodiode, because of the phase relationship between signal and reference signal, you measure S minus R times the complex conjugate. So if you do the math, you end up with a term that has the signal amplitude, the reference signal amplitude, and the phase difference between signal and reference. So if you know the reference amplitude and the phase of your reference signal, you can really get the amplitude of the field and the phase. And that's what's necessary to measure the amplitude and phase of your signal. So in a coherent receiver, you have basically two of these structures. So there's, again, this interferometric detection up here, and there's another interferometric detection down here, where there's an additional phase shifter. And this phase shifter allows you to measure not only the in-phase part of the signal, which is this part, but also allows you to measure the quadrature part of the signal. And the difference between those two is that once you have the cosine of the phase difference, and on the other you have the sine of the phase difference, so you can really recover a full 2 pi of the phase. So we are not yet there at the polarization diversity coherent receiver. That's on the next slide. So in this case, you basically need two of these IQ demodulators, which allow you to measure the in-phase and quadrature part of your signals. And the signals you're sending to these IQ demodulators is a signal split by a polarization splitter. So you have the X polarization up here and Y polarization down here. You mix both signals with the same local oscillator. So finally, you have 4 independent terms. So it's the in-phase part for the X-polarization, the quadrature part for the X-polarization, and the same, the in-phase part for the Y-polarization, and the quadrature part for the Y-polarization. So this allows you to do a full recovery of the electrical field, which you in turn need to do the polarization demultiplexing, which is the next slide. But before going to channel matrix estimation, I will briefly show how this looks in the instrument we have just recently introduced. So what we have down here is again the signal, polarization beam splitting, 2 IQ demodulators or 90-degree optical hybrids. We have a tunable laser source that acts as local oscillator, splitting this into 2 parts so that each IQ demodulator has its own local oscillator input. And then we have the 4 balanced receivers, the 4 balanced photodiodes. Then this goes to the A to D converters, and from that we have to do the digital polarization alignment or polarization demultiplexing. And once we have done that, we can do the digital decoding of the phase modulated signals and show whatever is interesting, so the spectrum, the IQ plot, whatever is interesting for the customer. So in this case, we have, for example, the constellation, the spectrum, and the I and the Q eye diagrams. And in the instrument, we have basically all the lower parts in the box beneath here, and up here we have the A to D conversion and all the signal processing. So joint spectral estimation is the problem we still have to solve, and there are basically 2 methods to do this. So you could either use training symbols or you could do a blind channel estimation. So what is training symbols? Training symbols are a special piece of information that is sent out from the transmitter, and the receiver knows that there's a special set of information coming in, and by knowing what is coming in, it's easier to do an estimation of your channel. It's quite efficient and it's widely used in the RF, but of course the receiver needs to know what training sequence is sent out, and there needs to be some synchronization to know when training sequences are really received. Since this method is not yet very well standardized or widely used, there's no common training sequence or detection scheme or triggering scheme, so that's not really feasible for a test and measurement gear. On the other hand, you could do blind channel estimation, which requires to have some prior knowledge about the signal. It does not require prior knowledge about the signal. All you need to know is the modulation format. It might not be possible to do a full recovery of the information, but we figured that this is probably the better choice for a test measurement instrument. But bottom line is really there is no ultimate solution for the problem as of today. So here's an example of a blind Jones matrix estimation using the Poincare sphere. So what we have here is sending out a QPSK signal we have introduced on the slide about complex modulation on the X and on the Y channel. And we're looking at the phase difference that's coming, that's sent out on the X and Y polarization, and what this means for the signal in the Stokes phase, where you can represent the polarization of your signal. So in case you send out a 0, 0 on the X and a 0, 0 on the Y, there's no phase difference between those 2 signals on the X and Y, those 2 signals. And the effective state of polarization you're sending out is linear 45 degrees polarized. Same is of course true if you send out a 1, 1, 1, 1 on Y. So always if you send the same signal, the same symbol on X and Y, you have linear 45 degrees polarized light. If you send out different symbol on X and Y, so for in this case a 0, 0 on X and a 1, 0 on Y, there's a pi-half phase shift between those 2 polarizations. So instead of polarization, this means you have right circular polarized light. That's of course also true if you have a 1, 0 and a 1, 1, or a 1, 1 and a 0, 1. So you have right circular polarized light for all these symbol combinations. If you send out 0, 0, 1, 1, that's this symbol and this symbol. There's a pi phase shift between the 2 symbols on X and Y, and you end up with a linear minus 45 degrees polarized light. And the same, of course, if you have 0, 0 on X and 1, 0, 1 on Y, you end up with a phase shift of minus pi half or plus 3 3 pi half. So this means you have left circular light. So in total, you have only 4 states of polarization coming out of your QPSK polarization multiplex transmitter. And those 4 states of polarization represented in the Stokes space represent those 4 points. And those 4 points in turn define a plane. And the normal of this plane you can use to do an estimation of your channel. Of course, if you send out single polarization light, there's only a single state of polarization. And this single state of polarization can also be used to rotate back your polarization in case you have only single polarization coming out of your transmitter. This is, by the way, a real measurement, and you can see that there is other polarizations on the transition from one state to the other. The question is, does that method also work for other formats? And can you use it, or what do you have to do if there's a time-dependent Jones matrix which would rotate those states of polarization versus time? So in this case, we have looked into a different modulation format. Here it's a 64 Quam format. So it's an example of a higher level Quam format. So in 64 Quam format, you have 8 amplitude levels on the in-phase part of the signals, and you have 8 amplitude levels on the quadrature phase of your signal. And if you look at the states of polarization that can be created using a 64 Quam signal on the X and on the Y polarization, you end up in the Stokes space finding these states of polarization. And these states of polarization are in a lens-like object. So there's always a plane defined by this lens-like object. And the normal of this plane is still defined, and you can use this normal of the plane to do your polarization demultiplexing. So the method in general does not depend on your modulation format, so it works for QPSK, but it also works also for 64 Quam and for other polarization, for other advanced modulation schemes. So we have to look into what happens if there is a time-dependent Jones matrix. So again, we look at the received signal. There's the inverse of the Jones matrix. This would allow you to get back to the original signal coming out of the transmitter. What you can do then, if you have received these two signals on the polarization, you can calculate the vector of the received signals to the nearest symbol in your constellation map. And this is basically, you have to define which is the nearest symbol, then you can calculate the nearest constellation. Then you can calculate the vector to the nearest point in the constellation map. And you can use this vector to update the estimate of your inverse Jones matrix, of your inverse channel matrix. You can do this iteratively, so you can improve your channel estimation for one symbol to the next symbol. So for this method, you of course need to know the constellation map. The update step you can tail, you can make it fairly fast, you can make it pretty slow so that it does not follow any noise. You can apply additional restrictions for the inverse of the Jones matrix. You have to, of course, worry. You might need to worry about whether this method converges for a bad initial guess, and locking speed might be slow, so you might lose some initial symbols of your transmission. And in the next slides, we will look into the decision-based estimation, how this really works, and what results we have found. But before doing that, look into the example, what happens if there's a large PDL on the transmission channel. So this is, of course, a transmission channel that's not working very well, because if there's a large PDL, then of course there's an iteration. But how does the math look like for that? And for making things a little bit easier, I've chosen an X-polarizer as the worst case PDL. So in this case, the channel matrix would look like that. So we have only a 1, so only the X polarization is preserved from the sent out signal. And if you do the math, then you would easily see that in this case, the denominator goes to 0, which means the whole channel matrix diverges and goes to infinity. So you cannot basically calculate the inverse channel matrix of an polarizer, so you only can calculate the channel matrix for a well-behaved channel. That means a channel that has not a very large PDL. So we have set up a model to study the decision-based estimation. What we started out again is a QPSK signal, polarization, division, multiplexed. We have again those 4 sets of polarization I've introduced the slides before, and that's a static state of polarization in this case. And by modeling the rotation or the fluctuation of your channel, we have chosen a very simple model of 2 rotating wave plates. And by rotating those 2 wave plates, we end up with a state of polarization that is moving around. We have only introduced the polarization rotation effects and noise in our model, and the dual wave plates are really the model of the channel matrix. So what we did is a fast rotation of the channel matrix at 25 megaradians per second, and the constellation before doing any corrections really looks not like any signal, so it's moving around very fast. The state of polarization, it's also moving around fairly fast. You cannot recognize the 4 states of polarization you would expect for a QPSK signal. But if you do the correction, then you can recover the QPSK signal in the constellation, and you can recover the 4 states of polarization you would expect for a QPSK signal. Down here we have shown the 4 channel matrix elements. It's a complex number, therefore we have the in-phase and the quadrature, or the real and imaginary part of the channel matrix elements. And you can see that this channel matrix element is moving around versus time. And we have 4 of those, therefore we have 2 elements up here on the left side, and we have 2 elements on the right side. Now if we add some noise to the signal, we still get a nice recovery of the constellation after the correction. We get a nice recovery of the state of polarization after correction, and we still have a very fast rotation of 25 megaradians per second, where in typical networks right now you would find only kiloradians per second. Again, we have basically the same estimation of the channel parameters, but there's of course some noise added to the parameters due to the noise of the signal. If we look into detail on one of the channel matrix elements, we can look how well this really tracks the theoretical expectation. In this case, we have looked into this element of the channel matrix, and the green is the theoretical rotation value we have set, and the black dots are the estimated values. And you can even see in the zoomed-in view that the channel estimation nicely tracks the estimated channel values. And the estimation, of course, and the noise in the estimation reflects the signal-to-noise ratio of the signal. So if you have a good signal, you have a good estimation. If you have a bad signal, then of course you would get a worse estimation. But you can still track at 28 dB signal-to-noise ratio a rotation of 25 megaradians per second. What's quite interesting, if you look into the solution in the channel estimation finds, you see an interesting property. The channel matrix is actually unitary, which means it obeys this relationship, and this relationship basically means that the power is equal in each polarization channel, but the total power is constant. But in this case, of course, because we have some restriction to the channel matrix, there's only 4 degrees of freedom for the Jones matrix, not 8. So we have to, if we restrict ourselves to finding a unitary matrix, we have only to find 4 instead of the 8 parameters of the Jones matrix. Here we looked into how fast it's logging to a final right estimation of the channel matrix. So we started with a stationary but misaligned constellation. So the constellation splits up into 16 points before the correction, and after the correction it's again the well-known 4 states. The state of polarization is again 4, but it's not aligned. After the correction it's aligned. And you can see that's only a few points outside the the correct estimation, so the estimation is converging fairly fast. There's only 2 points until you reach almost the final solution or the final estimation. So even if you have a very poor initial guess, the estimation looks very fast to the final estimation of your matrix. Now, what happens if you have signals that have bad signal-to-noise ratio? In this case, we have a signal-to-noise ratio of about 12 dB. It's a 6 gigabaud QPSK signal. It's a real measurement with a bad modulator. We're looking at 128 kilo samples. So it's a fairly long result, and it's not rotating in any case. So the received constellation looks like noise. There's no structure at all visible, but after the estimation of your channel matrix and after the correction, you can easily see the constellation on the X and on the Y polarization, and the signal-to-noise ratio of the original signal is recovered using this channel estimation. So the channel estimation works for stationary polarization, even for fairly bad signal-to-noise ratio of 12 dB. Well, if you start to apply some rotation on the measurement data, in this case we have applied 25 kilowatt per second, which is already a fairly fast rotation. In the network you would probably see lower rotational speeds. You still get basically the same received signal on your X and Y polarization. So the general estimation leads to correct demodulation for fairly bad signal-to-noise ratio and for fairly high rotational speeds. Now here we have a measurement example we did with the instrument, and this is also a snapshot of the screen you can have on the instrument. You can customize the screen. In this case we have the X polarization in the top row and the Y polarization in the bottom row. So we have the IQ plot, which shows the symbols as red dots and the transmission as green or light blue lines. On the right side we have the spectrum. So you can clearly see that this is a QPSK spectrum, and the width of the spectrum is roughly the 22 gigahertz you're expecting. The full scale is 26 gigahertz. So we have the same spectrum for the X and for the Y polarization. And in the middle we have the decoded symbols, which in this case, of course, doesn't make a lot of sense because there's clearly no constellation, so there's no proper decoding. But as soon as you switch on the demultiplexing, you get a nice constellation for the X and for the Y polarization. And then, of course, the spectrum remains more or less the same, but in this case, the decoded symbols really have some meaning. And in this case, you can also calculate some statistical data like error vector magnitude, quadrature errors, or IQ imbalance, which are statistical data you can extract from the constellation. So the demultiplexing really solves the problem of getting the original signals. If you have only single polarization, then of course the actual data rate is only half of it. So you have only the gain of a factor of 2 from the QPSK. So it's 21.6 gigabit per second. You have most of the signal coming into the X polarization. There's only a small portion of the signal coming onto the Y polarization. There's some different algorithm available so that you can basically rotate back the polarization so that all the signal is confined into one channel, and you can do all your measurements in this one channel. In the next webcast in this series, we will describe the quality rating of optical signal using the optical constellation diagram, which is this. And of course, this diagram can be described by a few numbers, as I've pointed out in the previous slide. There's quadrature error, which describes the angular distortion. But more on this topic will be in the next presentation in this series. So to conclude, we have seen that polarization multiplexing increases the efficiency by a factor of 2. The transmission over single mode fiber leads to crossback of polarization channels. So we need to recover the original signals in order to be able to demodulate the signals coming into the receiver. For that, we need to have a polarization diversity coherent receiver, and we have to estimate the channel matrix, which we can do using training symbols or blind estimation. The tracking of these changing channels is possible using advanced algorithms, namely these decision-based algorithms we have shown before, and instruments, as we have shown some screenshots, are now becoming available, which include the coherent receiver and the appropriate algorithms to do the channel matrix estimation. And that's the end of today's presentation. I only want to take your advantage, want to introduce a few more sources of information, you can find out more on the optical modulation analyzer from Agilent under these two websites. We have recently written a white paper on metrology of advanced optical modulation formats, where we are comparing coherent detection, frequency domain detection, or delay line interferometer detection of modulation formats, and we are comparing those, showing advantages and disadvantages of all the methods. There's an application note available on the website on digital modulation and communication systems. And if you want to see the instrument on a live demo, we are inviting you to ECOG 2009 in Austria, which is taking place in Vienna this year in autumn. So if you want to have a live demo, just come to ECOG. And finally, I want to point out that we are running this in a series. So there are two webcast series. This one is from the lower part, be ready for 4000G optical networks and components. And there's another series which is dealing on digital topics like HDMI, PCI, serial data. So if you want to find out more on these, just go to the website and look under Webcast Digital or Webcast Photonic. So I'm coming to my last slide. Next webcast on this series will be quality rating of optical signals using the optical constellation diagram. It's 3 weeks from now.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.